All right, so I know it seems like it's been a while. It was last Thursday when we first looked at systems of equations, and we covered two methods for solving them. First off, we looked at what does it look like when you have two linear equations at the same time. Of course, we put them on a coordinate plane. We saw it gave us two unique lines, and those two lines typically intersected at a point. And then our solution for that system was that exact point where they intersected. Of course, we had two special cases, parallel lines which never intersect. That gave us no solution. Then we had what happens if you have two of the same line, which always intersect, which gave us infinitely many solutions. But aside from those two special cases, most of them intersect at one exact point. Identify the ordered pair for that point, you have your solution. Now, we also discussed about how, although graphing was a great way to visualize the problem, it wasn't necessarily the most efficient in terms of finding the answer quickly, or even the best guarantee that you'd find the exact answer. Because as we know, with the coordinate planes I typically give you, we're looking through a relatively small window. And the guarantee that they're going to intersect exactly within that very limited space that we're peeking through is low, unless, of course, by design, it was created to be, or to work out in your favor. So because graphing isn't always guaranteed to fit in the graph that you have provided, we also included a second method called substitution. Now, substitution, if you guys want, I can pull that up real quick here. For substitution, I actually gave you a list of steps. This was in last Thursday's notes, and it was really kind of favorable if one of your variables was already by itself. And that was kind of the information we used then. We boxed it in. We replaced that variable that it was tied to, follow through our process, find one of the variables, use that variable to help us find whichever variable was left over. Because remember, the goal is still the same. We're still looking for that ordered pair where the two lines intersect. So the final solution is still going to give us both an x coordinate and a y coordinate. Now, of course, we did come across those two special cases, which if you're not looking at them graphically, if you're looking at it purely through the algebra, what would typically happen in those cases is through our process of solving, all the variables disappeared and we were either left with a true or false statement. So just a quick recap there. A true statement meant that we had two of the same line, which meant infinitely many solutions. So true statements told us that we had infinitely many solutions. And what I mean by a true statement is something like 5 equals 5. Well, of course, 5 equals 5, it is the same number. On the flip side, if we ended up with just a false statement like 5 equals 8, of course, 5 doesn't equal 8, therefore it's false. False statement means that there was no solution for that system. And then if we wanted to stretch that one step further, that must have meant that those two lines were parallel. So even when you don't necessarily know what's going to happen, if you follow the steps of substitution, either you're going to find the solution you're looking for, which is going to be that ordered pair, or you're going to run into a dead end, at which point you look at what's left and then base your decision off of that. So again, very quick recap of what we spent at least an hour on last week. If you want, feel free. You can always go back to that video. It should be posted in Google Classroom. I think I went back and did that. Someone asked about it over the weekend, and I realized, whoops, I recorded it, uploaded it, but forgot to update it in Google Classroom. I believe it should be up there if you will need to go back at any point and see some of those substitution problems. Or well, we did one regular one and then one for each special case. Feel free to go back and watch that whenever you need to. Today, however, we're going to add to our bag of tricks when it comes to systems of linear equations, and we're going to add our third and final method for solving them, which is called elimination. So the names are kind of clue you into what the process looks like. Substitution, we literally were taking a box full of information and substituting it in for one of the two variables we had, worked our way through, got our solutions. Elimination does exactly what its name suggests. Our goal really is to cause something to eliminate, and that something in our situation is one of the variables. Because what I kind of alluded to last Thursday as well was, in order to solve for missing variables, you have to have at least as many equations as you do variables. So if you have two variables, you have to have at least two unique equations. Otherwise, you're stuck. But what we're going to do here is we're going to use some neat little tricks, some manipulations, change it to where we can get it down to just one variable through this process of elimination. And then as soon as you find that first variable, it's going to feel a lot like last week, where we're going to drop it back into one of the original equations and find what we're looking for. Now, those of you who've looked ahead, I know I posted these this morning to Google Classroom. If you've got these open, if you looked ahead, I've broken it into a couple different cases.
I can't see mine's on Google Class.
I'm sorry, what was that?
I don't see the page that you showing day 12 on Google Class.
So I'll go back and double check it. Maybe I thought I clicked the button and didn't. So after the lesson, I'll go back and make sure that it is posted. And then I'll also make sure I get this video uploaded and posted along with it as well. Have you been able to see the past lessons, Angela?
Yes. The last thing they're showing is day 11.
Okay. So yeah, I'll go back after the lesson and see if it's a problem on my end. And then we can work that out. So thank you for letting me know, because otherwise I would have just been going through as if everything was fine. So thanks for keeping me on my toes. All right. So the notes for today, like I said, are broken up into special cases here. The first one we're going to start off is the most favorable case. I like to call it the perfect case, because it really is just begging for us to use elimination. And then we'll look at what happens when we need to change one of our equations. And then we'll look at the most involved case, which is having to change both equations. So we'll get to those. We're going to work our way up to that slowly. But first, our perfect case. So what it means by perfect case is that the two conditions we ideally like to see are already met. And those two conditions are that first, we want everything to be lined up into columns. And by lined up, I mean that the X terms are one right over the other. The Y terms are, one right over the other. So are the equal signs. So are the constants, which are those values that have no variables attached to them. So really, we want kind of like an old school addition or subtraction problem. We like those nice columns kind of sorted out for us. The second thing we need to see is that one of the set of variables, notice it doesn't say it has to be X, it doesn't have to be Y, but one of the set of variables must have opposite coefficients. So I know it's bolded, but I'm one for extra flair. So we want them to line up, and we want opposite coefficients. And what I mean by opposite is really just that it's the same value, just with different signs. So like 5 and -5, -11, +11. We want those to be opposite coefficients. And the reason for this is when these two conditions are met, we're going to add the two equations together, like I said, as if it were just a typical addition problem. And what happens is what we're left with is just a one-step equation that allows us to solve for one of the two variables. Now, once you have that variable, it's pretty quick and easy to just drop it back in, find the second variable, and write your ordered pair. So I know, again, also bolded, but I'm going to emphasize it as well. Don't forget, because I saw a few people, I think, get all the answers, but not write their last final answer as an ordered pair. Your final answer does need to be written as an ordered pair. So your X coordinate, comma, your Y coordinate, and then wrap it in parentheses. Because remember, we're describing at the exact point where these two lines are crossing. So again, we can talk about it all day. It's not until we see it in action that we start to tie together some meaning to these statements. So this is what I consider a perfect case. So you'll notice the two conditions I like to see. First off, the x, all of the things are lined up. The x terms are right above each other. So are the y terms. So are the equal signs. So are these constants. Everything's kind of neatly lined up as if, you know, I've sorted them and organized them to look pretty. The second thing that I need to see is that I need to see opposite coefficients on one of my variables. So does anyone happen to see where that is true? Sorry, I see you're talking, but I can't quite hear you.
+7.
With a 7? Well, some people see, so it depends which way. If you're looking horizontally, be careful. Sometimes students think, one's positive, one's negative. I'm looking for the same variable. Now, sometimes students look and see, one's positive and one's negative. Okay, closer, but I need them to be exact opposites. So where we'd actually like to look here is this time on the x's. So notice the top coefficient is -8. The bottom coefficient is a +8. That's exactly what I like to see. They are perfectly opposite of each other. So what that allows me to do, this being the perfect case, everything's already set up to create this elimination. I'm going to draw in a bar underneath, again, as if I'm setting up an old school addition problem. Off to the side, this is personal preference. I just do it to serve as a reminder later on, but I like to put a little plus sign off to the side. But I wrap mine in parentheses because I don't want to confuse it as if it's one of the signs that was originally there. It's just to serve as a reminder to say, hey, I'm adding these like terms together. But once I get that, I'm going to zoom in here real quick. I go through and add each corresponding column, since they are in fact like terms, to see what happens. Well, first off.
Yeah, I have a quick question, Josh.
Yes.
So coefficient, what does that mean exactly? I had to step away. You might have explained it.
Oh, you're fine. A coefficient is a number that is right in front of a variable. So x has a coefficient of -8, 7 is a coefficient of y, 8 is a coefficient of this x, -2 is a coefficient of the second y. So it's the value being multiplied with the variable.
Thank you.
Yeah, you're welcome. I think I've mentioned it maybe once a long time ago, possibly back in Unit 1, but it was very, very brief. It wasn't something that we actually wrote down specifically. So it's understandable that one probably slid through the cracks. So.
Hey, Josh.
Yes.
I can get in Google Classroom.
Okay. So. All right. So again, treating this one like an old school addition problem, adding together these like terms. First thing we'll see is actually the exact thing we were hoping to see. And that is what happens when we add -8x plus 8x. So that -8 plus a +8 is going to give us 0x. But as we know with zeros, 0 times anything wipes it all out. So 0x is just gone. So it's at this exact moment we see where the elimination method gets its name. -8x plus 8x causes these two terms to eliminate. They're gone. 0. Moving on to the second column here, 7y plus a -2y is going to give me a +5y. Being mindful of my signs as I go. My equal sign, can't really do much with those except just bring it on down. And I suggest, if at all possible, keep it as lined up as well as you can. And then on the right side of those equal signs, we have a -10, which we're going to add to it a -20, which is going to give me a -30. And just like that, again, this is the perfect case, so minimal work so far. We're left with a new equation, 5y equals negative 30. How do we solve this one?
Divide both sides by 5.
Perfect. Divide both the sides. I know this is a really short equation, but I'm still going to try to stay consistent here. Divide both sides by that 5 because the only variable that's left is a y, and to fully solve for that y, we need it by itself. So the 5 divided by 5 on the left simplifies to 1, leaving us with y. Negative 30 divided by 5 on the right is going to give me a negative 6. And just like that, I now know that for my solution, the y coordinate is a negative 6. Now, I'm only halfway done because we're looking for an ordered pair. We only have the y coordinate. We still need to find the x coordinate. Now, it's at this point that students get a little bit unsure because some people really like strict instructions. But at this point, I point out that I still need to find an x. And I have these two original equations before the elimination. Both of them have both an x, which I'm looking for, and a y, which I now know. So technically, I could use either one of these equations, replace the y with a negative 6, and when I solve for the x, I will find the same x regardless of which equation I use. So it's at this point I usually allow students to pick the one that looks easier, feels easier, seems easier. I also have some students who always pick the top equation or always pick the bottom equation. There's no better way. It comes down to personal preference. So if I was choosing it, what I would probably do, I'm going to use the top one here just because some of the values, I don't know. I actually have no reason why I would pick the top one over the bottom one. I think just because it's the first one I look at, I would personally use the top equation. Oops. So I'm going to just copy it down real quick. So negative 8x plus 7y equals negative 10. Got a question here from Marissa. She said, you said you were looking for x and we choose either of the equations and use negative 6 for y. Yes. So x, we know what y is. We're done searching for y. We now know the y coordinate is negative 6. So because we're still looking for the x, it doesn't actually matter which of the original equations, so long as that negative 6 slides into the y's position. What happens sometimes is I'll have students take this negative 6 and accidentally drop it in for the x and solve for y again. That creates a really weird mess. So make sure you know what your goal is. Know that you're looking for x, but also remember that you already now know y. So I'm going to take this negative 6. I like to get a little fancy here with my notes. Not that it's super fancy, but.
Hey guys, did you get my text?
Yep, we'll take care of it after the lesson today. We'll get you in there.
Okay.
So I have this top equation. That's the one I chose. Again, you could have chosen the bottom one if you wish. And when I get to the y, I'm going to replace it with this negative 6. So I'll have negative 8x plus 7. And instead of times y, it's going to be times the negative 6 equals a negative 10. I kind of got a little crazy there with my equal sign. See if I can remedy that real quick. So you'll notice what I'm left with is an equation. Yes, there's parentheses. We'll take care of that rather quickly. But all that's left in terms of solving is there's just an x, and that's what we're looking for. So not much to do on the right hand. Hopefully the parentheses catches our eye. We'll do a quick little mini distribution there. So 7 times negative 6 should give us a negative 42. Bring down your equal sign. Bring down your negative 10. And then remember, your goal is we're still looking for x. So now we're just going to solve it like we would any other equation. This one's a two-step equation. So it throws us back to our days of unit 1. So we're trying to get that variable by itself. So I'm going to add 42 to both sides. Oops. So on the left, negative 42 plus 42 is 0, which is gone. Leaves me with negative 8x. Bring down my equal sign. While we're bringing down the negative 8x. Yes, Marissa, you're right on track. You're probably a step ahead of me at this point. I'm kind of slow this morning. But on the right there, the negative 10 plus 42 is going to give me a positive 32. And my OCD is going to kick in real quick. Don't mind me while I quickly adjust this. To finish getting that variable by itself, we're going to divide both sides by a negative 8. Because I didn't design this the best I could, I guess, I'm going to write my answer off to the right here. The negative 8 divided by negative 8 becomes a positive 1, which leaves me with an x. And then 32 divided by negative 8 gives me a negative 4. Oops. Now, we have a value for y. We have a value for x. What order do I write them in?
-6 and -4.
Negative 6 and then negative 4?
No. -4 and -6.
Negative 4 and then negative 6. So good catch. So even though sometimes you may find the y first, the y coordinate always comes second. And if you need a little reminder, I'm going to squeeze it underneath here. X always comes before y. So my final solution is at negative 4, negative 6. Now, if I was to put this into a graphing software, it would run all the numbers. It would do it very quickly. It would graph 2 lines. But what would come out of it is if we looked at where those 2 lines crossed, they would be crossing exactly at the point negative 4, negative 6. Now, remember, that was the perfect case. It was really kind of set up begging us to use this elimination method. The 2 primary conditions were already met. Everything, the like terms, all the similar pieces were lined up nice and neatly. And we already had opposite coefficients on one of our variables. Now, as we know, it doesn't always work out in our favor. So now let's see what happens if it's close, but not close enough. So I'm going to try to summarize a little bit what this prompt already says. But like I said, it's going to be very common that it's not set up in our favor. Now you'll notice that this system of equations is already lined up for us, which is nice. It saves me from having to add or subtract things from one side to the other, move things around. So that, thankfully, I'm avoiding. But what I can do to get the opposite coefficient that I'm missing is I can use multiplication. Now, the reason I can use multiplication is because it changes things more consistently. Because when you use multiplication, you're essentially at the same time using distribution. And distribution kind of keeps things balanced. And as we know with equations, we really, really, really like balance. So what it'll allow us to do is it'll allow us to make a change to one very unique piece, and it'll allow everything else to adjust so that equation still remains balanced. So as it says there, we can multiply either equation by literally any number we want. So hypothetically, if I wanted to multiply, say, the top equation by 1072, I could do that so long as I did it to both sides and so long as I did my multiplication correctly. Now, that wouldn't serve me any purpose. It would make the numbers extremely large, and it wouldn't get me any closer to that opposite coefficient. So what it then goes on to say there in the prompt is that choosing where and what to multiply by is much easier when you have a goal in mind. So it is highly recommended, before we try to figure out which equation we're changing, how we're going to change it, we would like to decide which variable we'd like to eliminate through the use of opposite coefficients. And that's going to help us change maybe one of them, or later both of them, to reach the goal we're seeking. So let's take a look at this system here. Right off the bat, the first condition is met. My x terms are lined up, my y terms are lined up, my equal signs are lined up, my constants are lined up. That's good. Don't need to move anything around. But then I look a little bit deeper and I notice, again, focusing on my x's and y's, unfortunately, the x coefficients are -5 and 9. They're opposite in sign, but they're not exactly opposite. And then on the y's, I have a -8 and a -4 for those coefficients. So we're not quite there yet. If I were to add these together, so don't do this, so pause for a second. But if I was to say, oh, this is elimination, this is the perfect case, let me just go ahead and add these together. Again, don't do this. -5x plus 9x would give me 4x. -8y plus -4y would give me -12y. And then -10 plus 18 would give me 8. Well, the problem is, all I've done is create a third equation that still has two variables. I can't solve this. It doesn't get me any closer. So I really, really need those opposite coefficients that we conveniently had in the perfect case. So multiplication is the tool that I'm giving you. Can anyone think of anything you can multiply one of these coefficients by to make it the opposite of the other?
Do like a -1.
So where would you?
You could do it to either one of them, really, right?
Mm-hmm. What would it change? What's your goal?
So it's going to change your signs.
Okay.
So if I do the top one, it's going to make it positive. So when you do that, is it like you pick the top or the bottom line, or if you multiply it, you're multiplying both? Which one is it?
So like I mentioned in the prompt above, it really helps. So those questions you're asking would be answered more easily if we had a goal in mind. So let me actually take a step backwards. Is your goal to get opposite coefficients on the x's or opposite coefficients on the y's?
Okay, so these are already opposite, correct? 5x and 9.
They're opposite signs, but let me ask you this. Remembering multiplication is our tool, can you think of a number that multiplies nicely that changes a 5 into a 9?
Okay, no.
What
No.
about a 9 into a 5? Not easily. We'd have to use a fraction. We'd have to get creative. I don't want to multiply a bunch of things by fractions, though. So x's, we're going to say maybe not. What about the y's?
Okay, so would you want to do like times a -2 at the bottom?
And what's that going to accomplish? What's your goal? What are you
It's
trying to
going
make?
to change the 4 into a positive, and then it's going to be an 8.
So you're telling me if you can change a -4 into a +8, it would be opposite the -8 above it.
Yes.
Sounds good so far, because if you think about it, 4 goes into 8 exactly 2 times. So what Tierra has done, and Miranda's following along in the chat here as well, so we're honing in on it, is there's actually 2 changes that need to happen. First off, we know that a 4 can change into an 8 by multiplying it by 2. However, they are both negative, so we know that the sign of one of them also has to change. Well, multiplying by a -2 not only will change the 4 to an 8, but the negative to a positive. So because, again, it sounds like we just kind of, we're pulling things out of thin air, but our goal, I want that -4 to turn into a +8. The only way to make that happen using only multiplication is if I multiply this entire bottom equation by a -2. So everything else in that equation, in fact, is going to change. But the pieces I'm really interested in.
Did you get my text?
Yes, it got. I told you after the lesson, we'll take care of Google Classroom. So the 2 pieces that we're really focused on is the -2 and the -4. Again, everything else is going to change. And if you notice that I did specifically use parentheses here for a very specific reason. And that reason is that everything in that equation is going to be multiplied by this -2. And that's what gives us the balance. So Miranda's question is, and this is on every equation like this. Yes, if you can get by with changing just one. We were lucky here because one of the coefficients went into the other coefficient nicely. 4 goes into 8 exactly 2 times. That's why we chose the 2. We chose the negative sign because we also wanted the sign to change. This is still fairly convenient because it was kind of pointing us in a specific direction. What we're going to see on our third example here in just a little bit is that sometimes it's going to be a hot mess and we'll have to actually just change both of them. So Marissa's question here is, so the -4 needs to be multiplied to get +8 because you need the -8 to have a positive with it in the other part of the problem. Yes. So our goal is still the same. We chose to focus on the y's this time. And if the top is a -8, and if we can turn the bottom one into a +8, that's going to be where the elimination happens. So that's why we we said x's are going to be too hard. 5 doesn't go into 9 nicely. 9 doesn't go into 5 nicely. But the 4 goes into 8 exactly 2 times. No problem, Marissa. This is kind of an unusual thing because we're taking an equation and we're changing the whole thing. But you have to have a goal in mind because we can change an equation any way we want, but that's only helpful if we know what we want. So what I want here is that -4 to turn into a +8. So that's why I've highlighted it. Do you distribute the -2 to all of it? Absolutely, Marissa. So what's going to happen, and this is usually how I organize my own work, is I go off to the side here so I can kind of track my process. So I haven't touched the top equation at all. In fact, I'm just going to copy it down exactly as it was. So the top equation is still -5x minus 8y equals -10. The bottom equation, Marissa's already, suspecting what's about to happen, is everything in that equation, even all the way to the opposite side of the equal sign, everything clear through, which is why I wrapped it in parentheses, is going to now be multiplied by a -2. So the -2 times 9x is going to give me a -18x. The -2 times -4y is going to give me a +8y. And the -2 times the +18 is going to give me a -36. Now, what usually makes people a little bit uncomfortable here is, well, I see this is still the first equation, but this doesn't look like the second equation anymore. It is. Everything has just been scaled out by a factor of 2. So everything is twice as big as it was before, and that's because of the 2. And then the negative changed all the signs. So all the positive values became negative values. The negative value became a positive value. Now, the reason why I'm happy is because if I look at this new version of the same system, not only is it all still lined up for the most part, again, based on my handwriting, but I now have opposite coefficients on my y's, which means just like we did earlier on the perfect case, if I were to add these two equations together, something should eliminate. So the negative 5x plus the negative 18x should give me a negative 23x. And you're going to notice I am shifting it over here because I already know what's going to happen to my y's. Negative 8y plus 8y is 0y. But for our purposes, this is where the elimination method gets its name. The y variables are now eliminated. And then on the right-hand side, negative 10 plus negative 36 is going to give me a negative 46. And it's not the most interesting equation in the world, but it is easier to solve. All that's left now is an x, and we can solve it by getting it by itself. And to do that, we're to divide both sides by that negative 23. So the negative 23 divided by negative 23 is a positive 1, which we hide, which makes x appear to be by itself. And then on the right, negative 46 divided by negative 23 is going to give me a positive 2. So good news, that's the hardest part. As soon as you find one of the variables, it is very quickly going to help you find the other one. And in this case, the other one is a y. Now, does anyone, I claimed that we can use either one of these equations. Does anyone have a preference? Would you like to use the top or the bottom of the original equations?
Top.
Top one? Okay, I had no preference. So I'm going to take this top equation and I'm going to bring it over here. So I have negative 5x minus 8y equals a negative 10. And I now know that my x is a positive 2. So when I get to the x, I'm going to replace it with 2. So that would give me negative 5 times 2 minus 8y equals a negative 10. I'm going to guess here. Hopefully I get a long enough line here. Remember, we already have x. We're looking for y. So now I'm just trying to solve this new equation. Well, it's technically the first equation, but now that we know x is kind of replaced. So the negative 5 times 2 is going to become a negative 10 minus 8y equals negative 10. And then we run through our process. We have a two-step equation. We're getting y by itself. First, we're going to add 10 to both sides. Which leaves me with negative 8y on the left. Negative 10 plus 10. A little unusual, but we get a 0 here on this case. That's okay. Zeros are numbers too. And then last but not least, we have to divide both sides by this negative 8. Negative 8 on the left, of course, simplifies to a positive 1, which allows me to hide it. And then 0 divided by anything is always 0. The only thing that's left is once you find both your x and your y, regardless of the order that you find them in, always write your x coordinate first, your y coordinate second, because that's going to describe the exact point where they intersect. So I've got another question here. So if we have 8y, why do we have to solve for y again? Is that because we had to put the x in the equation that we found? So yes, so we're not looking for 8y, we're looking for y. So along that process, we were trying to get that y by itself. So I don't know if I quite answered your question. So we're not solving for y again. If you know 8y, you don't know y yet. Now, if you know what 8y is equal to, kind of like we knew what negative 8y was equal to at this step, we were able to then get that y by itself. But that's why we still had to use it in an equation form. Thought y was 8. Nope, so 8, we had an 8y, we didn't have y equals 8. So yeah, so it's very important. That's why making sure, however you choose to do it, make sure your work is organized so we don't lose pieces, and that's a mistake that I still make from time to time. If you lose a negative sign, if you lose your equal sign, or if it somehow jumps kind of out of alignment, it can make you feel like you solved for something, even though you're not quite done.
So I have a question. If we would have chose the bottom one, would it be the same exact answer?
You know what? That is a great question. Let me run through it real quickly to prove it to you. So you don't have to write this down if you don't want to, but let's say hypothetically we took the 9x minus 4y equals 18. We'd have 9 times 2 minus 4y equals 18. 9 times 2 is 18. Subtract 18 from both sides. I get negative 4y equals 0. Divide by negative 4. I still get that y equals 0. And that's by design, because this ordered pair, this x and y coordinate that we're looking for, has to be the same for both equations, because that is the point that is on both lines. That's what it means to be an intersection point. It's a point that is on both lines. So again, you don't have to jot that down. In fact, I'm actually going to cut mine out altogether, but just a quick proof that yes, in fact, if I had plugged that x into either equation, the same result would come through. So good question.
Thank you.
Yeah, you're welcome. These are kind of hard ones to really kind of work through in their entirety, because this is not the only way I could have solved this system of equations. There's technically, although they wouldn't be very efficient, there's technically infinitely many ways you could solve a system of equations, the same system of equations, by simply multiplying it by different values. Now, like I said, this was probably the most efficient path, but it's not the only one. So everyone sees these problems a little bit differently. So trying to find the way that everyone feels comfortable with, that's the tricky part. But for this one, with a little bit of work and only having to change one of the two equations, we found out that these two lines, if we were to graph them, intersect exactly at the point 2, 0, which if you think about it, that would be on the x-axis, if you wanted to think about that. But yeah, so this was still fairly convenient. We got away with changing only one of the equations because one of the coefficients went into the other very nicely. But of course, not everything works out exactly like we want every single time. So there's kind of a backup plan here. If you don't see how you can change both right away, you can change both into the same value by multiplying them by each other, which I'll explain here in just a moment. So there is an unfortunate point here that says that having a strong understanding of multiples of numbers can make our change easier here. So what I mean by knowing your multiples, this is the same thing that probably way back in grade school they had you practice. So they had, well, obviously we all know how to count by ones. Then they probably had you count by twos. So 2, 4, 6, 8, 10, 12. Those are all multiples of 2. If I count by threes, 3, 6, 9, 12, 15. Those are all multiples of 3. And the list goes on, and I could play around with all of those forever and ever and ever and ever, because all numbers have multiples. Now, if you're not comfortable with your multiples, this gets a little bit tricky, which is why I have this backup plan, this worst case scenario. But what our goal is to try to get opposite coefficients on either our X's or our Y's. Now, I'm going to push you guys today to try to see one without using the worst case scenario, but then I'm going to prove to you very quickly that the worst case scenario still would have resulted in the same solution. Because like I said, there's infinitely many ways you can solve it.
Watching a movie.
Hey, Josh, I got a question real quick.
Sure, Dustin.
Can you, since the 14 is a multiple of 2, can you use that to
So
solve for the X and the Y?
you're looking over here on this side.
Yeah.
So yes, technically you could change one into the opposite of the other, but what would happen is your constants would eliminate, but you would still have both the X and the Y. So you would eliminate part of it, but it wouldn't be one of the two parts that we're hoping for.
Okay, gotcha.
So think of the constants as just kind of being along for the ride. They're going to change, but we're not really focused on them as much as we are our variables. It's a good question.
I got you. All right.
Otherwise, this one would become a little bit easier because what's going to happen is we're going to think a little bit deeper.
Okay, gotcha. Appreciate it.
Yeah, no problem. So put the worst case scenario on hold for a moment. We'll come back to it. I want to push us to try to see if we can spot a slightly smaller or shorter route. And if we don't, then we'll also do the worst case scenario as well. I want to offer you guys some variety here. Excuse me. So let's get the obvious wrong answers out of the way really quick. So kind of going through that same process we used on the previous one. Look at my X's. Does 6 go into 8 nicely? If you're thinking in terms of multiplication.
You nicely need.
I could use other operations, but in terms of multiplication, I can't think quickly of a number that I can multiply 6 by to turn it into an 8. And the same for the reverse. I can't think of a number, or at least not an integer, that I can multiply 8 by to turn it into a 6. So my X's, I'm going to put those on hold. My Y's, can you think of a number that you could multiply 4 by to turn it into a 7?
No, you can't.
No.
Well, not Paul Senior, Paul Junior.
Technically, you would have to multiply it by a fraction.
I thought they told you.
As we've said, fractions, I don't like fractions.
I think that was getting the.
What about 7 into a 4? No, because again, these numbers don't go nicely into each other for X's or for our Y's. So what we did in the last one where we got by with changing just one of them is not going to work here. So I need to kind of take a step back and think, okay, 6 doesn't go into 8, 8 doesn't go into 6, but is there a larger number that 6 and 8 both go into? It's one that I often forget myself, but it's not too far from either of those values. Oh, sorry. Miranda, I should have paid more attention to the chat. So Miranda is saying that 6 and 8 both go into 24. And I would agree because 6 times 4 is 24. 8 times 3, also 24. So they do have something in common. They do have a multiple that they both share, which means, remember, multiplication is our tool. Using only multiplication, I could change both the 6 and the 8 separately into a 24. Now, it'll take a different number for each to accomplish this goal, but we can do it. So let's start to work through it. We may not have the whole answer yet, but let's start to see. So Miranda's thinking we can get 24s for our coefficients on our x's. So I'm going to wrap this top equation. What did we say we have to multiply 6 by to turn it into a 24? 4. I'm seeing 4s all through the chat. Dustin, I think I heard a 4 as well. So I'm going to multiply this top equation by 4. Now, before I get too excited, let's see what that equation looks like before we come back to the second equation. Try not to juggle too many things at once. So if we multiply the top equation by 4, 4 times 6x is going to give me 24x. 4 times negative 4y is going to give me a negative 16y. And 4 times 2 is going to give me an 8 all the way on the other side of this equation here. So far, so good. So our focus there, just to kind of color code it again, our main focus was we were really excited about what the 4 times the 6x would accomplish. That gave us our 24x. Now, still focus on the x's. What would we have to multiply 8x by?
This would be 3, right?
It would be 3, maybe.
-3, right?
Well, okay, so I heard 3.
I thought we were still trying to get the 24.
You're right. You want the 24, but let's not forget our other goal that not only do we want them to get into the same value, we do actually want them to be opposite of each other.
Okay, got you.
So 24 is great, but negative 24 would be even greater.
Okay. So we use the -3 then instead of.
So by changing it, by using a -3 instead, not only is that going to get the 24 we're looking for, it is going to make it negative 24, which is opposite of the one that's going to be above it. So the -3 times 8x is going to give me a negative 24x. The -3 times -7 is going to give me a positive 21y. And the -3 times -14 is going to give me a positive, what's that, 42, I believe. And I'm happy now, again, let me color code these real quick. Let's go green or pink. So again, our change here was mainly focused on the x terms because those are the ones we decided, hey, these both share a common multiple of 24. Let's try to get them into 24s. One of them we did have to adjust to make it negative, but that just required us to throw in an extra negative sign in there. It did change the whole bottom equation, but that's okay. Hopefully we've come to the point where we can agree that the entire equation changes. What we're focused on for a moment is what we want to change and specifically how. So we're excited now, though, because when I go to add these two new equations, which have just been scaled out a little bit by either a factor of 4 or a factor of 3, when I go to add these two new equations together, the 24x plus the negative 24x is gone. It's 0x, it eliminates. Great news. Then I go to the y's, negative 16y plus 21y, I believe gives us a positive 5y. Bring down my equal sign. And then 8 plus 42 is going to give me 50. And just like even all the way back to the perfect case we did before, we have a one-step equation. This time we're going to divide both sides by 5. And it's going to leave us with y equals a positive 10. So again, once you find the first variable, it gets a little bit easier. Now, knowing that y is 10, which of the original two equations would you guys like to use? Top or bottom? Top. Miranda, oh, and Marissa, first come, first serve. They're saying top, again, really comes down to personal preference, but we can use the top equation here. So I'm going to bring it over here to rewrite it. So that was 6x minus 4y equals 2. Now that I know that y is 10, so I'm going to bring this up here. When I get to the y, I'll swap it out. So that rewrites this equation to be 6x minus 4 times 10 instead of y equals 2. My little guideline in here. And then I just run through my process. Get that variable by itself. Solve it like we would equations back in Unit 1. Parentheses hopefully are calling our name first. So negative 4 times 10 is going to give me a negative 40. Two-step equation now. I'm going to add 40 to both sides. Gets rid of it on the left, leaving me with 6x. On the right, 2 plus 40 should give me a 42. And then last but not least, still trying to get that x by itself, I'm going to divide both sides by 6. I should end up with x equaling 7.
Okay, so you take like the original, I see. So it makes it easier really if you take the, so it's not as many, it's not big. So I did the top one, but I did the bigger numbers and then now I understand. Okay.
So
it's
instead of using the original top equation, you used the slightly
Yeah.
adjusted one. So you should have still gotten the same answer. Is that correct?
Yeah, I did.
Good. And you should, because this top equation, the 24x minus 16y equals 8, is the exact same as the one we started with, just grown by a factor of 4. You should still get the same result there. So as you already pointed out though, Tiara, these numbers are significantly smaller, which means if I didn't have a calculator handy, maybe I could do it a little bit faster, but they should in fact give you the same answer. I apologize, guys. I see in the camera today. Wow, crazy hair day. So again, like I said, there are so many routes that these problems could take. It's almost impossible to really cover, to barely even scratch the surface. But yeah, so no, not bad on this one. Don't forget though to write your final solution as an ordered pair. And in this case, we should get the ordered pair 7, 10. Now, I mentioned earlier that there is this worst case scenario, which could save us if I get stuck. Excuse me. So let me copy it down real quick so I can do it off to the right here. And you can either write this down if you wish, or just follow along, because I'm not going to follow this problem all the way through. I just want to show you that it can kind of help you get unstuck. So the worst case scenario, I should show you here real quick, says that if you're stuck, pick a variable and multiply each equation by the opposite coefficient. Be sure to consider your signs during that multiplication process. So if they're the same signs already, one of them will have to change, so on and so forth. But what that means then is if I looked at the 6 and the 8 and I forgot that they both go into 24, I could instead multiply them by each other. I can multiply the top one by 8, the bottom one by 6. I would have to remember one of them needs to be negative though. Technically, doesn't matter which, but that would give me a positive 48 and a negative 48. Opposite coefficients, add them together, solve it out. You'll get the y, you'll get the same answer. Alternately, maybe I don't see that with the x's, or I say, oof, 48's too big. Okay. Well, then I look at the -4 and the -7 on the y's. Well, if I multiply the -4 by 7 and the -7 by 4, well, one of them is going to need a sign change because they're both negative. But then -4 times -7y will give me a positive 28. 7 times -4y is going to give me a negative 28. I'll still get opposite coefficients. So the worst case scenario is nice if you're having troubles with your multiples, because at the very least, you can multiply them by each other. So there's always a backup plan. So hopefully that alleviates some stress there. But also the good news is, just like a regular class day, I'm going to keep the Zoom open even after our lesson. So if you get stuck on one, I can help you guys get unstuck. So ideally, if you can find a multiple that's relatively small, great. More power to you. It's going to be a little bit easier. The numbers are going to be a little bit smaller. You can work your way through it. If that doesn't work, though, the worst case scenario says multiply the coefficients by each other, either on your x's or your y's. Don't accidentally mix them. It'll get you unstuck. If you find a problem like that later on, though, and you're still kind of stuck, let me know, and I will gladly work with you guys on that. But I want to make sure we have time to knock out these notes here. And of course, a lot of this has been building up to most people's favorite, word problems, application problems, real world problems, whatever you want to call them. This is where systems of equations are actually applied. So, couple things here. First off, quick disclaimer, because I've yet to go back and fix it because the math still works, the story just doesn't quite match. When I created this problem, I made it to where the student tickets were more expensive than the adult tickets. So that aside, yep, that's not going to make sense to the story, but that doesn't mean we can't still solve it. Because really I'm interested in the process, not necessarily the answers themselves, because this isn't a real world problem, it's a fictional one. But what I want you to notice is the only thing that has changed here is you haven't been given the system. The process is still the same, but you haven't been given the system. We actually have to write the system ourselves to then use either the elimination process or elimination method we learned today or the substitution method we learned last Thursday to solve it. So the only extra step is to write it. But anytime you're going to write anything, equation, system of equations, anything, it's a very, very good habit to define your variables first. Because if you're going to have even just one variable, you need to know what that variable is representing. So at the end, when you say x equals 5, are we talking 5 children, 5 tacos, 5 cars? I don't know. Label your variables so that you remember at the end what they actually signify. Now, for this one, because I like to take a few shortcuts when they make sense. I already know what I'm looking for. I've already provided those answer lines there at the bottom. So just to save myself from having to write more than I necessarily need to, I know I'm looking for the price per adult ticket. I'm going to say that'll be my X. And the price per student ticket will be my Y. Now, some students usually say, but Josh, can I use A and S? And sure, you can use smiley faces and triangles if you want to do. Variables are variables. They just serve to represent things I don't know yet. I like to try to stick with X and Y, particularly because when you start to get into some of the other alphabet, for me at least, my S's look a lot like 5s. My lowercase L's look like 1s. Try to think of some other ones. My lowercase b's, or at least my daughter's lowercase b's, look like sixes. So there would be some letters I would say maybe try to steer clear from. But for me, I'm really boring, I guess. I like to just stick with the X and Y's I've been using this whole time. And it doesn't really matter so long as I know which one is which. So X is going to be representing my price per adult ticket. Y is going to be representing my price per student ticket. I'm going to pause there for a moment because I know some of you are writing this down by hand. I'd like you to have a chance to do that, and then we'll jump into solving this. So hopefully you had a moment there to jot what you need down. The good news is we're going to strip away a lot of this story really quickly to boil it down to the system of equations that I'm looking for. So in case you haven't had a chance to read it yet, it says that Elisa's school is selling tickets to the annual talent show. On the first day of ticket sales, the school sold 12 adult tickets and 6 student tickets for a total of $157.92. The school then took in $118.26 on the second day by selling 11 adult tickets and 3 student tickets. Find the price of an adult ticket and the price of a student ticket. Now I know this, you're thinking, why wouldn't the school know what they were charging for at the beginning? Yes, absolutely. Let's assume though that we are looking back 20 years in the past. All we have are the record sheets. We don't know how much it was charged per ticket. All we know is how many tickets were sold. We know how much they made. And maybe we're the IRS and we're saying, hey, wait a second, where'd all this extra money come from? Again, we could, there's a scenario in the world out there where this could apply. So a little of imagination will help us out here. So throwing it all the way back to what I've said a couple times now, we have 2 variables, which means in order to be able to solve this successfully, we're going to have to write at least 2 unique equations. Now, what I usually recommend is find a way to group the information in a way that it makes sense. So any ideas here? Any ideas? If you want to jump straight into an equation, that's fine. Talk me through your thought process. Any ideas? How can we start grouping this information together?
I was thinking maybe one equation would be for the first day, you can have 12x plus 6y equals 157.92.
Absolutely. And Miranda's supporting you in the background on the
Yes.
chat. So absolutely. So it kind of makes sense that, well, they've already kind of recorded all the sales for day 1, and it really ties together both of our variables. Why not use that first day as my first equation? So that sounds great. So that would give us 12x, because that was 12 adult tickets at whatever unknown price. That's what we're looking for. Plus 6 student tickets, again, at some unknown price y. That's the other thing we're looking for. And this equals the total for that first day or first night of $157.92. I feel like I wrote extremely small. I apologize there. So good news is we've used all those values, and that took care of day 1. What's day 2 going to give us then?
11x plus 3y equals 118.26.
So I like that you didn't, some people are so tempted to write it out the way that it is worded in the problem. And you are actually, whether you realize it or not, Dustin, you're thinking ahead to when we need to solve it. You're already thinking that, oh, I want these to line up. Why would I not write it so that that is already happening?
Right.
So great idea there. So 118.26. Good. So even though the information for day 2 was kind of given in reverse order, we've written it so that our system is nice and pretty. And so for our purposes, I'm actually going to go ahead and pretend like there's no story anymore. I'm going to say, okay, let's ignore the story. Let's just assume this is the system of equations that said, hey guys, let's solve it. And let's work through our process that we were using earlier to see if we can work through this successfully. So right off the bat, is everything lined up for us? Seeing some heads? Yep. And Dustin, it's all thanks to you. You worded it in a way that it was written out nicely. Second thing we need, do we have opposite coefficients on either the x's or the y's?
You can use a 6 and a 3.
So you're looking at the 6
Two.
and the 3, but
Yeah.
so technically though, right now, there's no opposite coefficients.
Right.
yet.
Right. Yeah. No.
But you're looking at the part that's going to allow us to change or to get away with changing just one of the equations. What's so special about the 6 and the 3, Dustin?
They're both divisible by 2.
They're both not
Well,
quite. You're on the right track.
Not divisible, but 2 can go into each one of them.
So you're getting closer. You have the right information. We're just wording it differently. So it's not necessarily that 2 goes into each of them, but 3 goes into 6.
Right. Right. Yeah.
Times.
Yeah.
So, and Miranda's in the background here, kind of backing you up as well. So I would agree if I multiplied that 3 by a 2, that would give me a 6. But Miranda's also pointing out that we probably want that to be a negative 2.
Right.
Because if they were both positive 6y's, they wouldn't eliminate. They would just get
Right.
bigger.
Yeah. True.
So by multiplying the bottom equation by a negative 2, that is going to get us one step closer to eliminating one of our 2 variables. So the top equation, I'm not going to touch. So I'm going to copy it down again. The bottom equation, though, everything's getting multiplied by this negative 2. So watch all of your signs, watch all of your multiplications carefully. And you may want to have a calculator nearby because we are dealing with money. So there are some decimals, not to be alarmed. So negative 22x, negative 6y, and here's where I would grab a calculator as well. 118.26 times a negative 2.
That is only 236. Negative 236.
Negative 236.52. And I'm happy now because the y's have those opposite coefficients that we're looking for. So just like all the other problems, again, we're pretending there's no story here. We're just solving a system. When I go through to add these 2 equations together, the y's are going to eliminate because 6y plus a negative 6y is 0. The 12x plus negative 22x is going to give me a negative 10x. And then the negative 236.52 plus the 157.92 is going to give me negative 78.6.
Hey, Josh. I got 157.92 times negative 2, and I got negative 315.84.
So you got to be careful there, Agat, because we're not actually multiplying the top equation. So the 157.92 stayed the same. It was the 118.26 that we multiplied with the negative 2. So that's where the negative 236.52. So you just grabbed one of the wrong numbers is all. So good job checking there, though. Okay. So yes, there's a decimal, but it's still just a one-step equation yet again. So when I go to finish this problem, excuse me, divide both sides by negative 10. I'm going to get that x equals 7.86. And again, yes, there's a story, but we're pretending that's not there. So for now, I'm just going to say that x is 7.86 because we're not quite done yet. We still need the y that goes with it. So your guys' choice. Do you want to use the top equation that we wrote or the bottom equation?
Let's use the bottom, switch it up a little bit.
Bottom equation, switch it up. I appreciate that because otherwise, sometimes students think, oh, he always uses the top. I must not be allowed to use the bottom. So good call there. So I'm going to rewrite this equation over here. 11x plus 3y equals 118.26. And now that we know what x is, we're gonna drop that into this equation. So I'm gonna have 11 times 7.86 plus 3y equals 118.26. So again, it may be handy if you're a little bit uncomfortable with decimals. You may want to have even just a basic 4-function calculator nearby, but our process is still going to be the same. So we're going to take that 7.86, we're going to multiply it first by the 11 because the parentheses should catch our eye, and that should give us an 86.46. Hopefully you guys are fact checking me as we go. Plus 3y equals 118.26. Then I'm still trying to solve for y, so I'm going to subtract the 86.46 from both sides. So at this point, really the only annoying thing is that it takes so long to write. That's okay, don't get lazy on me. Laziness is where we make silly mistakes. So it leaves me with 3y on the left. On the right, again, hopefully you guys are checking me. I believe gives me not negative 31.8.
Yeah, 31.8.
And then the only thing that's left to do is to divide both sides by 3.
It'll be 10.6.
10.6. Now, I'm going to go ahead and put 10.60 because technically you can add as many zeros at the end of a decimal as you want without changing the value. But you guys probably already know why I like it that way, considering we're talking money, because when we zoom out, we then remind ourselves, well, hold on, we're not just looking for a point where two lines intersect. X and Y actually represented real information. Well, real information. So X is the price per adult ticket. So it turns out that they charged adults $7.86. Yep, that's a weird thing to charge. It's very specific. And then the student ticket is $10.60. Also equally weird and equally specific, and even more weird because rarely do you see student tickets being more than adult tickets. Usually there's a student discount. But again, if you rewind, if you're watching the video, I had a disclaimer at the beginning that this was my bad. When I made this, I think for whatever reason, I actually got my variables switched when I wrote it. So yes, in the real world, it doesn't quite fit scenarios that we're probably familiar with. But in the terms of this fictional world, apparently students pay more for their tickets, and apparently they charge very precise rates. But we solved it, and this would work in any situation like this. So the only new thing is we had to write our own system of equations. How we actually solved it was the same exact way we solved every other.